talking about structs. So using structs to structure related data, a struct or a structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you are familiar with an object oriented programming, a struct is like an object's data attributes. In this chapter we will compare and contrast tuples with struct to build on what you already know and demonstrate when structs are a better way to group data. We will demonstrate how to define and instantiate structs. We will discuss how to define associated function, especially the kind of associated functions called methods, to specify behavior associated with a struct type. Struct and enums discussed in chapter 6 are the building blocks for creating new data types and in your program domains to take full advantage of Rust compile type checking. Defining and instantiating a struct. Structs are similar to tuples discussed in the tuple type section, in that both hold multiple related values. Like tuples, the piece of a struct can be different types. Like with tuples in a struct, you will name each piece of data so it's clear what the value means. Adding these names means that structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the value of an instance. To define a struct, we enter the keyword struct and the name struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Then inside curly brackets we define the name and types of the pieces of data which we call fields. For example, listing 5-1 shows a struct that stores information about a user account. Okay. To use a struct, after we have defined it, we create an instance of the struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then adding curly brackets containing key colon value pairs, where key are the names of the fields and values are the data we want to store in those fields. We don't want to specify the fields in the same order in which we declare them in the struct. In other words, the struct definition is like a general template for the type and instance field in that template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5-2. So here we are getting object of the user struct. To get a specific value from struct, we use the dot notation. For example, to access this user's email address, we use user1.email. If the instance is mutable, we can change a value by using the dot notation and assigning it into a particular field. Listing 5-3 shows how to change the value in the email field of a mutable user instance. So using dot you can change the value. Note that the entire instance must be a mutable. Rust allows you to mark only certain fields as mutable. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. Listing 5-4 shows a build user function that returns a user instance with the given email and the username. The active field gets the value of 2 and the sign in count gets the value of 1. So fn build user email string username string and we are returning the user. Okay, it makes sense to name the function parameter with the same name as the struct fields, but having to repeat the email and username field names and variable is a bit tedious. If struct had more fields, repeating each name would get even more annoying. Luckily, there is a convenient shorthand using the field init shorthand. Because the parameter name and the struct field names are exactly the same in listing 5-4, we can use the field init shorthand syntax to rewrite build user so that it behaves exactly the same but doesn't have the repetition of email and username as shown in listing 5-5 fn build user. So a build user function that uses field init shorthand because the email and username parameter have the same name as struct field. Here we are creating a new instance of the user struct which has a field named email. We want to set the emails field values to value in the email parameter of the build user function. Because the email field and the emails parameter have the same name, we only need to write email rather than email colon email. So it is kind of like what we have seen in JavaScript, right? creating instance from another instance with struct update syntax. It's often useful to create a new instance of a struct that includes most of the value from another instance but changes some. You can do this using the struct update syntax. First, in listing 5-6, we show how to create a new user instance in user 2 regularly without the update syntax. We set a new value for email but otherwise use the same value from user 1 that we created in listing 5-2. Let user 2 equal to user, and we have created this particular user using struct update syntax, which we can achieve the same effect with less code as shown in listing 5-7. Oh, okay, so you can update. Nice. So here is the struct. Okay, and here I have created a user 1. If I want to update user 2, I can just write something like this. The code in listing 5-7 also create an instance in user 2 that has a different value for email but has same values for the username, active and sign in count fields from user 1. The there are only three dots. I think in JavaScript there are three dots, and in Rush there are only two dots. Sorry, must come last to specify that any remaining field should get their values from the corresponding fields in user 1, but we can choose to specify values for as many fields as we want in any order regardless of the order of the fields in the structs definition. Now that the struct update syntax value equal to like an assignment, this is because it moves the data just as we saw in ways variable and data interact move section. In this example, we can no longer use user 1 after creating user 2 because the string in the username field for user 1 was moved into user 2. If we had given user 2 new string values for both email and username and thus only use the active and sign in count values from user 1, then user 1 would still be valid after creating user 2. The types of active and sign in count are types that implement the copy trait, so the behavior we discussed in stack only section would apply. Okay, so if I try to print user 1, I will get an error, I think. Okay, so user 1 dot active. No, it works. Note the above struct update syntax uses can no longer use user 1 after creating user 2. Okay, let me try to run this and see. Cargo run. Maybe it works. Maybe I can't use email, I guess. No, I can use that as well. I'm not sure what they are talking about. I think what they are talking is let user 2 equal to user 1. If we wrote something like that, then we won't use able to use user 1. Using tuple struct without name fields to create different types. Rust also supports structs that look similar to tuples called tuple struct. Tuple struct have added the have tuple structs have the added meaning the struct name provides but don't have name associated with their fields. Rather, they just have the types of the field. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples, and when naming each field as in a regular struct would be verbose or redundant. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here we define and use tuple struct name color and point struct color struct point. Okay, and when we are creating object of this, we are using something like this. Note that the black and origin values are different types because they are instances of different tuple struct. Each struct you define is its own type, even though the fields within the struct might have the same type. For example, a function that takes a parameter of type color cannot take point as an argument, even though both types are made of 3i32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot followed by the index to access an individual value. Unit like struct without any fields. You can also define structs that don't have any fields. These are called unit like struct because they behave similarly to uh, unit, the unit type that we mentioned in the tuple type section. And unit like struct can be useful when you need to implement a trait on some type but don't have any data that you want to store in the type itself. We will discuss traits in chapter 10. Here's an example of defining and instantiating a unit struct. Name always equal to define. Okay, this is a unit struct. To define always equal, we use the struct keyword, the name we want, then a semicolon. No need for curly brackets or parentheses. Then we get an instance of always equal in the subject variable. In a similar way, using the name we defined without any curly brackets or parentheses. Imagine that later we will implement behavior for this type such that every instance of always equal is always equal to every instance of any other type. Perhaps to have a known result for testing purposes, we won't need any data to implement that behavior. You will see in chapter 10 how to define traits and implements them on any type, including unit like structs. Ownership of struct data. In the user struct definition in listing 5-1, we use the own string type rather than the ampersand str string slice type. This is a deliberate choice because we want each instance of the struct to own all of its data, and for that data to be valid for as long as the entire struct is valid. It's also possible for struct to store references to data owned by something else, but to do so requires the use of lifetime, the rust feature that we will discuss in chapter 10. Lifetime ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in struct without specifying lifetimes, like the following. This won't work. uh, Struct user. Okay, then I have created a user object of the struct. The compiler will complain that it needs lifetime specifiers. Yeah, because we are using a slice string instead of a string. In chapter 10 we will discuss how to fix this error so you can store references in structs, but for now we will fix error like this using the own types like string instead of references like ampersand str. You can use ampersand str in struct fields, but you will have to use lifetimes. So try to use string. Yeah, I think my net went down. So that's it for today's video. Thank you for watching. See you in the next one.